I'm going to start today learning in dynamical systems. AKA LLMs. So that's what I'm going to start today, and probably it's going to take us until the end of the course to develop this kind of theory, which I think is very interesting and very new. A few notices. So I believe you have an exercise. When is it due? Today? Thursday. So due to request, I'm giving you an extension till Tuesday, the week after that. I think there will be one more exercise. It's going to be very small because we only have 2 weeks, I guess, after that. So it will be a 2 weeks, very short exercise, and that's it. Then exam. We're done. Any questions about administrative things or something I forget? This Thursday, I'm away, so no class. So 2 days, day after tomorrow, there's no class. And then we have 4 more classes where I hope to wrap up this learning in dynamical systems. Any questions, comments, anything administrative? All right. So thus far, our tour has taken us through online learning, in which, Kara, hi. I announced the exercise is due Tuesday. We started with online learning, prediction from expert advice, and decision-making / learning when we have no environment model at all, purely adversarial setting, which was a very beautiful setting, but it's very simple, and we got very simple algorithms with very clean guarantees. And we continued through optimization and statistical learning, boosting, various other models for learning without a state. And then around mid-course, we switched to learning with a state, where we talked about dynamical systems and Markov decision processes. And just last week, we talked about the LQR model. What I want to do today is look at a new model for learning, which is inspired by the success of these LLMs, or AIs, that we see right now. Many of you have seen the new AI documentary that just came out, and in fact, I've seen with some of you who have been in the same theater with me. It was a lot of fun. It's beautiful. I really highly recommend it. They do say there that the way AI is being built is by training. I forget who said that, maybe Benji or one of the characters in the movie, real life people in the movie, say that it's built around next token prediction. So what does it mean? We give the LLM a sequence of words, for example, learning in dynamical, and then it has to predict the next word here, system. And according to that, the parameters of the model are being fed feedback, a gradient feedback, correct or incorrect, turns out into a gradient, and the parameters of the model are being updated in such a way that they predict the next token more and more accurately. This is how we train LLM. Some of you, like here are building these from scratch. Okay? That's exactly how we train them. And it doesn't seem like this will result in anything useful. At least a priori, it didn't seem like it. I think before ChatGPT 3, I don't know how many people believed it's going to give rise to such intelligent behavior, but it did. This is a theoretical machine learning class, which means I will try to reason about this phenomena from a theoretical point of view. So what is the model? The model is that we have a dynamical system. For example, this person here. And it's a very complicated dynamical system. Then we have input coming in, U1 to UT. And we have output tokens coming out, Y1 to YT. There is a feedback loop, so the next token will depend on the previous one. For example, when I'm speaking, you're all trying to guess what am I going to say in the next, all of you know, word, right? That's what I'm going to say. The next word I'm going to say is word. So this is the setting. Very complicated black box here. Tokens, inputs, outputs are simple. They're simple, relatively simple. We can represent a word in the dictionary, in the English dictionary, there are roughly 200,000 words. And if you take all words in all languages, including some numbers, and so Google scale type systems will have maybe 10 billion such different words in their vocabulary, and then they represent them in a vector space, which is roughly a few thousand dimensional large. So not huge. So each y t lives in some r to the d, and d is maybe a few hundreds, a few thousands. I think in your model Kia, it's maybe 1,000, roughly, 800, something like that. Yeah. So standard models, Llama and so on, Elmo, these have maybe a few hundred or a few thousand dimension of word embeddings. And input is the same as output, same domain for LLMs. You can have, of course, much higher dimensional input-output systems, such as videos, in which case you have an image, and then that is also usually many times downscaled via ConvNets or via some other technology to something in much more manageable space. Okay? So that's what I'm thinking of. So inputs and outputs are not in huge dimensional space. They're in a few hundreds, a few thousand. And in the setting of learning in dynamical systems, the goal is to predict the next token very well. So maybe we see U1 to UT, Y1 to YT, and we predict some Y hat T plus 1, and the goal is to minimize summation from T to T, some loss function having to do with YT and YT plus 1 hat, YT plus 1 and YT plus 1 hat. For example, this can be mean square error. So this should remind you the protocol for online learning or online convex optimization, right? We have a sequence of iterations. Every iteration we've seen, we know all the history, and we're trying to predict the next token. We take a guess, and then we see the actual truth, we suffer a loss, and repeat. What did we do in online convex optimization? We competed with a class of predictors, usually. So we had, in OCO, YT hat was generated by some machine, maybe parameterized machine, over the past Ys, and used. Sometimes it used the past, sometimes it didn't. And it was a simple rule. For example, it was like theta transpose, maybe xt, maybe I see some, or something like that. Maybe xt is a context that I see the this iteration, and then I predict linearly according to it, and so forth. And then usually we measure regret compared to the best data in hindsight, but there is absolutely no assumption about the sequence of y's that are being observed. Yeah, everyone with me so far? What's different in this setting compared to online learning? Yeah? Laya?
Well, one thing I was going to ask, but maybe is also answering your question. In online convex optimization, you can take any point in your space, but here, actually, your vocabulary is a set of points within the space which you need to map to. You can't just take any arbitrary point in RD.
Okay, so your concern is that my output has to belong to one of the vocabulary points.
I don't know if it's a concern, but it's a technical defect.
Yeah, I mean, we could think of various ways to resolve that. I don't think this is a huge problem. For example, I could take the convex hull of all of these points and then project to that. Or I could just say, you know what, I don't mind if it's outside of the convex. I just want to predict the y hat. Whether it has a meaning or not, I don't really care. I'm still going to minimize mean square error. That's still a legitimate thing to do. And then if you actually want to predict a word, you can take the closest point to it, or the closest vector that corresponds to a word in that space, and so forth. So there are various ways to amend it. I would say that's not the biggest difference from OCO that I'm now thinking about. What is different about this setting where I'm trying to learn a human being. So I have some person in the box. Elijah is in the box. And I'm talking to him and he's talking to me back, and I want to predict the next word he's saying. Okay? This is a setting of online learning, but in what sense is it different from what we have seen? What's the different characteristic here? Yeah, Edward?
There is some structure in time.
Absolutely, there is structure. What is the structure? You're right. Yeah, Connor?
There's a causal structure?
Yes. There's a causal structure, that is correct. Or maybe in the words that we have learned already, or in the mathematics that we have learned. What is the property of the sequence of tokens? Yeah, they're all observations from a dynamical system. Okay, so here is the new component. Yt is a projection, some nonlinear projection of xt, where xt evolves according to some dynamics from a previous state, and maybe the inputs, and maybe some noise. What is this xt? So there is a state. The state is what's going on in Elijah's brain right now. And that evolves from iteration to iteration, and when he decides to, is this offensive? It's not
No,
offensive.
please
Okay,
go on.
okay. If it is, I will say myself. So then he is speaking, he's saying, oh, go on. That means that that's his character and all of his personality, and his parents brought him up in Michigan. Where did you grow up? Massachusetts. And all of that goes into his character. Look what a nice guy he is. He's laughing about it, and all of that came through. It's not random. It came from somewhere, and where it came from is his brain. So his brain have all these weights that have been trained all his life, and now when he's speaking the next word, like I say, hello, Elijah, he's going to reply to me, hello, or whatever. Hi, I don't know what he's going to say, laughing. That is some response that is a result of the input that I'm telling him, and he is hearing through his ears, go to his brain, process through all the weights of his brain, and then something comes out. So that's how I choose to view this problem. It's not a standard viewpoint, okay? I'm telling you some new viewpoint that I'm currently studying or promoting with my colleagues, and I think it's an interesting way to view how we do sequence prediction. So this is an assumption that did not exist. Okay, it's an assumption. I'm assuming something about my data that I did not. It's a generative model. I did not assume that when we talked about online learning, or we talked about statistical learning. We said, oh, statistical learning is a completely degenerate setting where we have a distribution and things get sampled from that distribution. Clearly, that's not what's happening, I hope, when I talk to any of you. You're not just sampling words. You have some thing in your brain that generates words that I'm interested in hearing. Every single one of you going into Princeton, that's a very hard thing to do. You probably have a lot of intelligence in there, and there is the sequence of words that you're generating is very informative. It's very special. It's not random. It doesn't come from any distribution. Does this make sense? Comments or concerns? Yeah, Jeff?
It comes from a distribution, right? Are you saying that it just doesn't come from a random distribution, or are you saying it doesn't come from any distribution?
Well, distribution is a very general term. So that's true that you can make it encompass basically anything. But in what sense is it a distribution?
Like Leventhal is not like the actual vector, right? It just predicts distribution over the vocabulary. And so in that sense, like I'm saying. Yeah.
Oh, that's a totally different thing. If you're saying that this Y is a distribution over words, yeah, that can be, it doesn't have to be a deterministic word, even though at the end of the day I am saying a word. I'm not saying a distribution of word. I'm saying an actual word. But maybe my brain has some distribution over words that I'm about to pick what to say, and that's totally fine. This Y can be a distribution over vocabulary vectors. That's fine. Or embedding of vocabulary vectors. That's fine. This is very different from a word being chosen from an IID distribution. When we talked about statistical learning theory, we talked about for example, classifying images in MNIST. This was by the way, the person who wrote MNIST, Jan LeCun, is here today. He's going to be giving a talk at 4:30. I highly, highly recommend. He's one of the best scientists of our generation. So,
Where's the talk?
I believe it's at Friend 101. I don't know why it's not advertised.
I think it's
Maybe
in
it's a
Share.
secret? It's what?
I read online it's shared.
Share it 101?
Yeah, it's an Orphe talk, right?
It is an Orphe talk, but somehow I'm private with some private information. I mean, I get the email, but I think it said I will check. Before the lecture ends, I will check.
I said friend.
Friend, right? Yeah,
Orphe needs to update the website.
good. Saved you. Well, it's going to be crowded. So, I was at MNIST, okay, MNIST, Jan LeCun. We have these digits, and then the model was these digits are sampled from some distribution in nature. Nature, there is some distribution over digits. And I wanted to find a hypothesis that if I sample another image from the same distribution, I will do well in terms of error. That made sense, maybe. I have all these, it was a post office, United States Post Office problem. They wanted to sort automatically the zip code of letters. And maybe they have a distribution over letters, and maybe it's not pretty stationary on a year by year basis. So for a given year, I see a letter, yeah, there is some distribution over the digits over there. And then it makes sense to come up with a hypothesis that will classify them on that distribution. When we talk about learning in language, I don't think it makes sense to say that every token we hear comes from a stationary distribution. That doesn't, in my opinion, it doesn't make sense. There is a time evolution of the dynamics that created it. Does it make sense? Of course, you can talk about changing distribution or distribution over brains, or that language is pretty broad. You can always encompass it. It just doesn't capture the main features of the problem.
I don't know if I agree with that, because can I not see digit prediction as just like really, or can I not see language prediction as the same as digit prediction, except the number of classes I have is just like, is the number of classes is no longer like just 10 digits, but it's just the entire vocabulary.
Entire vocab, but then if you sample from it, so remember PAC learning is IID distribution. Okay? So this means when you generate, whatever distribution you pick over vocabulary, if you generate IID from it, it's going to look very different from language. That you agree. If every single word I'm going to pick IID, you're not going to get Dostoevsky from that. You're going to get some string of things that it will look gibberish. I don't think it will make sense at all.
Can you not see it as like, you take distribution over like k-gram characters, where it's like the number of k-grams is like
Okay.
really large.
That's already a different story. So you can say maybe there's a distribution over n grams, yeah. So, and then that's a much more complicated distribution, and then it's IID maybe over. It's not even exactly IID over n grams, because you sample an n gram, you're going to get an n words. The next n words, it's not that you complete n words and then see another n words. The way it would work is you move one, and then you say what will be the most likely completion for the n minus 1, right? So n-gram model is actually much closer to this, I would say, than to IID. You agree? Okay, so you're fine now. You agree with me. That's good. But I like this debate. Any more questions? The n-gram point was very good, I thought. You see, because there is a causal structure, right, that's moving along. So the next word is not going to be just IID. It's going to depend on the past, whatever, n minus 1 words and completion of that. Yeah. Objections? Everyone with me? I'm kind of surprised. I was happy that Jeff had something to say, but I'm also happy if more people have kind of comments about it. I'm very happy to hear. Yeah, David.
I think you still could fit in the statistical learning approach if you, for example, model distribution over all possible outputs.
Outputs meaning sequences or?
Sorry, all possible sequences if you consider the entire sequence as one output. So sequence
Yeah.
until end
Yeah.
termination.
Yeah. Yeah.
But then you'd get less strong results than you would probably here.
Okay, David's point, let me repeat his point. David is saying I could view it in statistical learning model where the distribution is over documents, not over words. That is a strong point. In fact, one of my colleagues, Natis Rebo, says that. I think this is, you can view that, you can view it this way. Of course, it's a very complicated distribution. So you have now distribution over What is a document? For example, my book is a document, or this lecture is a document. It's from start to end, a sequence of sentences. It's not a single sentence is not a document. So if I upload this video to YouTube, the entire transcription is going to be one document. Distribution over these kind of long documents is a very complex creature, and I don't know that you can make too much sense about that algorithmically, if it makes sense. So just the number of parameters here is so large, it's not clear to me how you would learn this kind of distribution. A. B, this distribution, even though it does capture structure within the document, it's hard to see how you would learn to complete a document if you learn this kind of distribution, right? If you just learn a distribution, I have one distribution, oh, Dostoevsky and Tolstoy. Now I see half Tolstoy. It's equally probable I will complete it Anna Karenina and, War and Peace. It's going to be equal. So you don't take into account the inner document dependencies, which I think are important. Okay. Make sense? Elijah?
Since you're inviting dissent, I
Yeah.
just want to be clear. Are we talking about what is a good way to model LLMs or a good way to model language?
At this point, I'm not distinguishing between the two.
Okay, I
Yeah.
think that that's a very strong claim. And my intuition for why that is like a very strong claim is I feel in my own perception of my own language that I very rarely am going token by token. I think that when you say I don't see a difference, I have set myself on a goal of the meaning I'm trying to convey.
Yeah.
And then I form a sentence around the meaning rather than sampling my way through the sentence.
I like what you're saying. You're introspecting. Elijah's point is the following. He's introspecting and saying, when I want to make a point, when I'm speaking, I have a point I want to convey. And then I choose the words. They somehow come naturally. It's like I'm driving a bicycle. Okay, I want to get to my house on the bicycle. I know where my house is. I know how to move my legs. Now I can listen to YouTube on my phones. I don't really need to think about it. It's kind of automatic. That actually fits very well within what I want to say, because there is a state. And that state can change very slowly and give rise to kind of the sequence of output tokens. So in that sense, that fits well. There is another thing you said, which, do I distinguish language from LLMs? And I said, I don't make a strong distinction at this point, in the sense that I think this framework is interesting to learn language, to learn LLMs, to learn humans, to learn meteorological dynamical systems, to learn differential equations, to learn many things. And the reason I'm saying it is that it's, I think, pretty much a fact now that LLM are very successful at learning language. I think they nailed it. They nailed it better than many people. So in that sense, I think it's just a fact that they are able to learn language well. Okay.
I think it depends on what we mean by language. Because if we mean, are you able to compose coherent sentences that read well,
Yes.
it's undeniable. But if in our conception of language, we have this dependency on having a point to make, having our own perspective that we want to convey, I think that's probably much harder to say that LLMs have done.
I agree. I think it's still true for LLMs. They're able to make a point. They're able to reason. And at this point, I would say it's undeniable there is intelligent behavior happening. To which extent you think they're very intelligent, they're somewhat intelligent, they're just stochastic. I don't know. There are various opinions. But those who say it's stochastic parrots, I would say you're out of it. I mean, that's a losing argument. At this point, it's clear that they have intelligent behavior. I think you would agree with me that they exhibit intelligent behavior.
So that's the distinction between exhibiting and actually doing it, right? And I'm not sure, but I'm saying, like, if you want to say that they...
Okay, we became very philosophical.
Yes.
So, okay. I mean, the viewpoint I like to promote is I'm of the same opinion as what Turing said when he talked about intelligence test. It's functional. So it's hard to say, is this person intelligent or not? I don't know. You might be a robot masquerading as Elijah, but to me, you have the same behavior and you say intelligent things. Yeah, you're Elijah, from my perspective. You're intelligent. So that's kind of the viewpoint I prescribe to, but now we're getting into completely, I'm not going to make any formal claim about that or any rigorous claim, okay? So we're much more into philosophy. I do want to argue the following. This is a model that's powerful, trying to predict the next token in a sequence, and the sequence is generated by a dynamical system, and it's interesting. Whether you agree with me that it captures every little detail having to do with language generation or not, I accept. There could be other interesting models. Maybe it doesn't capture everything, maybe it does capture very little, but I still think it's an interesting model, captures some of it. So under that assumption, I'm going to continue. I'm happy about the descent. If there's more descent, I'm also happy to hear it. But I think philosophy, we're kind of exhausted the philosophy for now. Yeah? Good. So this is the framework of learning in dynamical systems I'm going to study. We have a sequence of tokens that are generated by a dynamical system. It has a state. The state can be huge, like this person here. It's very complicated. Dynamics are very complicated. And I don't know how to, or I don't want to, learn maybe the F and the state. They're very hard to learn and reconstruct, such as in this example. So I don't want to do that. But I do want to be able to predict the next token very well. That I want to do. So I will get to this goal, even though it looks like a very scary goal. So I will show you an efficient algorithm that's able to do this, exactly this. Okay, in a very general setting. But this will take me a few lectures. So I want to start now with a goal which is the same goal and the same setting, but a simpler setting. And that simpler setting is going to be linear dynamical systems. So let's start with learning linear dynamical systems. And by learning and generation, I mean exactly the same thing. So we have a sequence of tokens. We have the system, input U, output Y. Maybe there is feedback. But inside is ABC. There is no, maybe ABC is a good model for a person, but it's more degenerate. So how is YT generated? YT plus 1. YT plus 1 is AXT plus BUT, maybe plus noise, WT. And what is, sorry, this is XT plus 1. And then YT plus 1 is the projection of XT plus 1. So this is the model. If you remember, this is exactly the same model we talked about on last Thursday. But last Thursday, we had full observation. We decided that Y is equal to X. We didn't have the C projection here. For my purposes, this C is critical. It's critical now that we have partial observation because this can give rise to much more complicated behavior that is much more difficult to decode than if I see the entire state. If I see the entire state, maybe it's much easier. But I could have a very complicated thing behind the hood. So X can be huge, A can be huge, B, all of these things are huge. And I just see the sequence Y, input U, output Y. Yeah?
So does that mean C isn't invertible? Because if it were, you could just take Y and find X.
No, it's not. Usually C is a projection. So X is an R to the million, trillions, and then Y is a scalar, for example. Okay. That's the scale I'm thinking of. Now suppose I see a sequence Y's, right? So the setting is so I see U1 up to UT, Y1 up to YT. Then I predict YT plus 1 hat. Then I see YT plus 1. Then I suffer, let's say, mean square error. Okay? I don't know A, I don't know B, I don't know C, I don't know X, I don't know nothing. Okay? And now my question is, can this be done? So suggestions. I'm open now to suggestions from the public on how to do it. How can I do it? Is it clear what I want to do and why it's interesting? Yeah, Ben.
You can try to minimize regret against, like, essentially gravity.
Okay. So Ben is suggesting the following. How about we minimize regret or optimize? Best predictor in a class. And if I understand you correctly, the class that you're suggesting is maybe pi is a policy mapping past inputs and outputs to the next one. So pi is going to be parameterized by ABC of u t to 1, y t to 1. This notation means y1 up to yt, u1 up to ut. And this is going to be basically what's written here, so without the w's. So maybe it's going to be xt plus 1 is axt plus u, ut, and then yt plus 1 is going to be cxt plus 1. So what does it mean? If I unroll this recursion, this is a recursive formula. This means yt plus 1 hat is summation I from 0 to t, c a to the I b ut minus I. Is this what you meant, Ben? I think this is what you meant.
Yeah.
Yeah? So I can try to basically learn the best predictor in this class. So this is parameterized by ABC. And given use, sequence of use, I can output the y hat and see if I got ABC right, I will get the output right in noiseless setting. Make sense? Kara, question?
Can you do it like lower dimensionally in your model system? Like are the agents here probably lower dimensionally?
Very good. So if I want to learn this kind of predictor, I need to know the A. Knowing the A means I need to know the dimension where X lives, the hidden state. And I don't know any X. I never saw any X in my life. I only see the Y's. I only see the token when you talk to me. I never saw your neurons in the brain and all that. So I don't know the dimension of A, right? That's what you're saying. I agree. So this is not completely well specified. I guess I could specify, oh, I'm guessing the A is 10-dimensional. Try to learn it with the data. So that's what I will try to do. Then 10 doesn't work, try 100. 100 doesn't work, try 1,000 until it works. Yeah, you're right. There is a, so problem 1, which Kara noted, is that this D of A is unknown. Is this the only problem? Anyone has another issue with this? Yep.
Even if, suppose you did know D, it might just be a very high dimensional problem.
Yes, that's right. So unknown, I agree. Problem 2. So D can be huge. Yeah, problem, also problems. But suppose I tell you D and it's 10. Is that okay? Can I solve for ABC? No. Yeah, Alex, why?
Well, if we're learning it with gradient descent, do we know that it's convex?
Oh, very good. We know that it's not convex. So problem 3, this is not convex. Because I have a polynomial of degree 3 here, you see? A multiplies B multiplies C. There's no reason for this to be convex. It's actually not convex. Okay, so 3 problems, okay? I cannot really, it's not a practical thing to do for these reasons. So, but still a good suggestion is actually sometimes people still do it, despite all of these objections. In fact, I would say that's the common thing to do in classical control theory. And that's because they handle very low dimensional problems, so you can make it work. But when we talk about high dimensional problems, forget it. This will never work. Both suggestions? So I'm going to, this is classical. This is a good policy class also. And in some sense, it's the This is the generative policy class. I mean, we know that there exists a policy of this form parameterized by ABC, which actually has zero error or up to the noise. We know that because that's my assumption about the data. So another suggestion. What else can this is problematic. Another suggestion? Yeah, Joshua?
Is it possible to just learn like the linear map from like the U space to the Y space?
Very good. So suggestion 2, linear map, linear predictor. So I can try to learn yt plus 1 hat to be summation I from 1 to t mi ut minus I. Yeah? Very good. This solves 2 of the issues here. So d is unknown, who cares? I don't care what d is. D is huge, also who cares? This m depends only, is input by output dimension, so it's small. Still there is a bit of an issue here, which is, as I wrote it, there are too many parameters, right? I need to go all the way back to the past. So here I had 3 parameters. This is great, actually. This is a succinct model. It can be learned statistically. You can argue about it from statistical learning theory. And the VC dimension, the dimensionality of the problem is 3. It's possible to learn it. As I wrote it here, I need t parameters. T is too big. Okay, so the number of parameters grows with time. That's a problem. So what do? Okay, let's chop it. I think this will be the next kind of, let's say h, some parameter h. And we chop it at h, try to learn a linear predictor. How can we learn a linear predictor? Well, all ungraded descent is a good way. Maybe we have these parameters here, h parameters. This is a convex predictor. If I look at the square loss as a function of m1 to mh, it's going to be convex. I can run all ungraded descent. We know the regret bound, square root t. Yeah, this is great. I can learn it. But, question, so everyone okay? This is a good suggestion. This is fine. I'm happy with it.
I guess my question is like a priori, so you could learn something, but would you have any guarantee that it would do well?
Very good. So why would it do well? So question, which h, if at all, works? Works meaning that it gets the loss goes to 0. Not clear. If I take h to be t, yeah, I mean, it's expressive enough because I can just take all, you see here, this is a linear predictor. I mean, I could call this mi, then it is a linear predictor. But number of parameters is too big if I take h to be t. So what can I say? Any ideas? Or is it clear even what the issue that I'm raising? Important issue. Yeah?
Yeah, can you re-explain one more time why t would be too big? Like, are all the previous states bunched up into one U? Or why is the number of parameters too big?
Yeah. The question is, why is it problematic that if I take h to be t, if I try to do a linear prediction for the entire past, why is that problematic? Yeah, Jeff?
Because when you try to generate a sequence of, like, say, like 100 million parameters, and if you try to generate, like, a sequence of 1,000, you get 1,000 parameters.
Correct. So the number of parameters grows with the iteration that I'm trying to predict. Do you remember when we analyzed the ungraded descent? How did our regret look like? Our regret looked like square root t times dg, right? The gradient bound and diameter. What is well, gradient bound is not a problem, but diameter, how does the diameter scale with number of parameters? Linearly, right? So there's going to be a t here. That's going to ruin the regret bound is going to be vacuous. That's technically where it comes in. You're not going to get around it by any other method. There are just too many parameters here to learn. If you have as many parameters as data points, you will overfit, right? You will overfit. We talked about this overfitting issue in the past. So this also happens in statistical learning theory. When we have as many parameters as the number of data points, we overfit. Okay? That's exactly what would happen if I take h to be t. Is this clear?
So, like, if going back to the practical application of an LLM, is this equivalent to like using a context window, like to
Yes, it would mean context window of the same size as my data that keeps on growing with my data,
Okay.
as much data as I have.
Okay, okay.
That's what it would mean.
That,
So it never ever stops. There's, yeah,
that makes sense, thank you.
yeah, sure. Yeah, you good? Everyone clear with me? Everyone okay? So suggestions, what should I do? Yes?
Well, what I was kind of thinking was like, we kind of saw, like, so last class we were talking about how if the spectral radius is small, then or sorry, if it's less than one, then the norm decreases exponentially. So it's kind of just like if you have,
Very good.
even if you chop off the
Yes.
views from a long time ago, it's still not really going to be that much. As long
Yes,
as-
yes. What Alex is saying is correct. He's saying that if the spectral radius is less than 1, this A will basically shrink. Shrink, shrink, shrink. At some point, it doesn't really matter. It doesn't contribute much to the y hat. And in fact, it shrinks geometrically fast. So yeah, we don't, effectively, we could lose less parameters. This is correct. What you're saying is correct. I don't want to go there, even though it's absolutely correct. The reason why I don't want to go there is because for many examples, you don't have shrinkage. Maybe the spectral radius is 1, or maybe it's 2 even. I don't know. Maybe this thing explodes, or when we speak, the norm of my volume stays the same, or whatever. The norm of the words I'm speaking stays the same, no matter how long I speak. And we wanna do capture long context, so that's why I don't. But still, that's not strong enough reason that I'm saying here. It's just that I planned the lesson with something else. That's the main reason. But what you're saying is a good suggestion. It's a valid. This is a valid assumption to make here. Yeah.
But that would sort of restrict the kind of systems we're learning, right? So
Absolutely.
it's-
Absolutely.
Then if I say
Absolutely.
what
Yes.
is important at the start and then talk for a long diatribe and then
Yeah.
ask what was the important thing, then you won't be able to learn that in those sorts of
Correct,
applications.
correct, correct. So it would, what Alex is suggesting would restrict the class of linear dynamic systems I would learn, absolutely, but it will give me a rigorous learning methodology, and that's a nice trade-off to do, and I think it's a very useful thing to have, absolutely. Jerry?
It's just kind of a random idea, but I was thinking like, so now we have kind of, I guess, a linear regression problem. And I was thinking like, is there a way to regularize it where you say, because we know the ends have to follow a structure where there's like a multiplication by A.
Yeah.
So is there a way to use that to like come up with like another regularization constraint?
I think you're getting back to Ben's suggestions of learning the kind of the parameters, the ABC, or imposing structure on the M's in some way. That's one way to take it. The other is perhaps what I'm getting to. So, yeah.
I mean, it seems like if we cap age at really any point, you kind of like lose the dynamics at some point. It's almost like it's periodic. Like if you blow a leaf and it goes
Yeah.
really there, it doesn't matter
Yeah,
if this is
yeah.
like repeated, you kind of lose track of it.
Yeah, yeah, yeah. It seems like this would have like infinite memory, right? That's what it seems like.
Or yeah.
But is that the case? So try to think into your linear algebra class. If that's really the case. There is a nice linear algebra trick I will show you. So theorem. Class of linear predictors. So this means yt hat f1 hat summation I from 1 to h n I ut minus I plus summation j from 1 to k n j yt minus j. So I'm incorporating not only the u's but also the past y's. This is very important. So I'm kind of taking a bit more power to my hands. So it's linear, a bit more, kind of taking more information, but it's legit. Okay, legit. For h and k to be d, that's the dimension of A, learns pi ABC. So it learns the LDS class. this I mean that you can get zero error. If I take h and k to be d, then the class of linear predictors, it's convex, that's great. I don't need any assumption about spectral radius, it's always true. And I just need to take enough parameters, but it doesn't grow with t. It gets stuck at some point, d. Then I can learn it in OGD as a grid, something like d root t, and such that average regret and loss go to 0 as t goes to infinity. So it's able to learn in the sense of next token prediction exactly. Exact learning. Is my theorem clear? Should I make it more precise? So by that I mean, let me write it a bit more precise. So 1 over t, summation t from 1 to t of y hat, which is basically this. Goes to 0, t goes to infinity. And in fact, it's like 1 over root t. D over root. So if I predict using this predictor here, and update it by Orlan gradient descent, it's an efficient algorithm. The loss goes to 0 for any dynamical system. Theorem clear, folks? Any questions about the theorem? Do I need to spell out the algorithm, or algorithm is clear? I can write down what the algorithm is, okay? The algorithm is I see the yt. You want me to write the algorithm? Okay. Let's write down what the algorithm is. Algorithm. So I see ut, then I compute yt plus 1 hat. I see ut yt. No, just ut. I compute this, so summation I from 1 to d ut minus I plus summation j from 1 to d and j yt minus j. Then I see yt plus 1. Then I update nt plus 1 are gradient of with respect to m and n of yt plus 1 at mn minus yt plus 1. That's the algorithm. It keeps on, it sees the u, it predicts, then it sees the actual y, then it updates. It updates the m and n according to Orlan gradient descent. This is a convex function of m and n, right? And this algorithm satisfies that the loss goes to 0 if indeed the yt's, this is under assumption. So assuming that the yt's are basically come from an LDS. From some LDS, unknown LDS. Yeah, okay, algorithm okay? Questions? There is, of course, it's like, this is updated by the gradient. There is a 1 over root t here, and you know, all of all OGD algorithms we studied before. So that's how we update it. Is this accurate enough? Or if you want me to, I'll write it a bit more explicitly, the gradient update. Is this okay, folks? Yeah? Questions? Do you see why this is surprising? I mean, I think it's surprising. Do you see why it's interesting and surprising? Yeah? It's non-trivial, right? It's a non-trivial statement. Questions? Yeah, Jeff?
So, how fast do I do this though? So like if I roll out from like some X now, and then I roll out really long, and then like learn this with
Oh, well, I wrote the regret is d root t. So this means,
or like and then if I like shoot some other X now, like it's fine. Right?
doesn't matter, from any x. From any x. X doesn't even come into here. There's no x. I just see y's and u's, and my claim is that the regret is d root t. It can be made a bit more precise. It's dg root t. The g, these are the gradient of the quadratic loss and the diameter and all that, which we went through it in the first part of the course. It comes out to be roughly d root t. And if you take I think maybe 2, maybe there's factor 2 there. So divided by t, you'll get d over whatever, 2d over t, root t. And this means after t being roughly 2d over epsilon squared iterations, you're epsilon close. Your average error is epsilon. No matter where we start from. So it's a very strong theorem in my opinion. Yeah, you agree? Elijah at least agree. I don't know if the rest of you agree.
I want to see the proof.
Okay, I think proof is very nice. Very, very, very cute. Yeah, David?
I feel like it's a limited situation. Like
Okay.
what I was trying to think of like counter arguments.
I'm so happy about the proof. You're telling me it's a limited situation. Why is it a limited situation?
I was thinking of like, for example, learning white noise,
Uh-huh.
or learning things that are very hard to learn, learning
Yeah.
things with very long context.
Yeah.
But then I realized that you can't. This doesn't say anything about that
Correct.
because
Correct.
A is limited dimension.
Very good. So look, white noise does not come from a dynamical system. That's the pinnacle of what I want to say in terms of dynamical learning. I cannot learn white noise. Who cares about learning it? You know, I want to learn interesting things. Interesting things came from you guys when you speak to me, or from whatever weather that I can observe and take measurements of. It all came from nature, which means there is an underlying dynamics, and these are the type of signals I want to learn. So by making these assumptions, I think I didn't lose anything. That's my opinion. You can make it stochastic and add noise and so on. I'm going to leave that for homework. But that's a small thing. Yeah? You agree? Okay. More comments? Okay, so this is a very nice, sweet proof in my opinion. I hope I will try to get it done. So, to recall your linear algebra days, I have a matrix A in R d by d. It's d by d because it takes the input space to the output space. It's a square matrix. It doesn't have to be symmetric or nothing. There is no other restriction for it. It doesn't have to be spectral radius, or any matrix, doesn't matter. I can write the characteristic polynomial for it, PA of lambda. This is the product over I from 1 to d, x minus lambda I. This is PA of x. So lambda I are all the eigenvalues of A, and I take the product of them. And this is all, even if there are multiplicity of them, that's fine. It's always well defined. And it always exists. Okay, this kind of thing always exists. Yeah? I just defined it here. I showed it to you, it exists. So now, there is a nice theorem called the Cayley-Hamilton theorem. And it says the following. I can think of this polynomial as a function of a matrix. Okay? So I can, for example, take P lambda of M. That's going to be product of M minus lambda I identity. Okay? That's what it's defined to be. So I can basically take, I plug in M instead of X. So the variable becomes a matrix. It's kind of a weird thing, but it's well defined. I mean, I can take product of matrices, that's fine. Yeah? And then I get an output, which is also, this is a function from matrix to matrix. Kind of seems a silly thing to do. But you'll see in a minute, it's a good thing to do. And what the Cayley-Hamilton theorem says is that, PA, is that PA of A is 0. It's the 0 matrix. It's an important thing. That's the only thing I'm going to use. remember this? No? So let me prove it to you. It's a very simple thing, actually. So let's proof. So assume A is diagonalizable. If it's not diagonalizable, the same proof will work with Jordan form. I just don't want to mess with it. So A is some U, D, U inverse. Okay? Now, let's plug it into this form. So I have PA of A is product over I from 1 to D. And here I have U, D, U inverse minus lambda I identity. And now I can pull the U times U inverse is identity, right? So I can pull this out. I can take this U times product I from 1 to D. And here I have D minus lambda I identity. Now let's look what happens at the jth entry of the diagonal of this matrix here, U inverse. Inside here. So what is this matrix here? Well, this is a diagonal matrix. Yeah? It's a product of diagonal matrices. What happens in the JJ entry? Well, I have the diagonal. Diagonal is going to be just all the eigenvalues there. So every diagonal is going to be cancelled by one of the terms here, by the lambda i's. Right? So they all get zeroed out. So this whole thing is 0, and then the whole thing is 0. Yeah? Everyone with me? Yeah? I don't know if you remember it from linear algebra, but I remember the name, Cayley Hamilton, but that's it. It's a very simple thing. But it's a very powerful thing too. So let's use that. I'm going to use that now to prove my theorem. And the way I'm going to prove it is the following. Let's write down what xt is. xt is equal to a xt minus 1 plus b ut minus 1. And then I can open it up more and more and more. So let me open it up. This equals a to the d xt minus d plus summation I b ut minus I. And then I go from 1 to d. A to the I b ut minus I. I from 0 to d minus 1. Yeah? Okay? I just unrolled the recursion. Now, let me write the same thing for xt minus I. So for I from 1 to d minus 1, I'm going to write all of these, just expand them. And I'm going to expand them until I get x to the a to something, xt minus d. So this is going to be a to the d minus I, xt minus d. Plus some bunch of j from 0 to d minus 1 minus I, a to the j, b, ut minus I. Some stuff, some remainder terms. Okay? But there are at most d terms in each of them. There's no more than d. There's less than d. Okay? Good. So now, let's remember our characteristic polynomial, p of lambda. And I wrote it like this, but I can write it in some form. This is summation I from 1 to d of I from 0 to d. So ai x to the I. And a0 is 1. You all agree, right? And then it's some mumbo jumbo of the eigenvalues. Doesn't really matter what the expression is. There is some coefficients. That's all I care about. Now, what I want to do now is let's look at summation ai xt minus I. Okay. Yeah. Well, just multiply all the, oh, you're right, AD. AD, I guess, is 1, right? So if you multiply all the x's, it's 1. Yeah. But this theorem, the fact that P8 is 0, this means that a to the d equals summation I, AI, a to the I, basically, I from 1 to d. Right? That's what it means. Negative. Negative. Okay, so let's look at negative summation AI xt minus I. This equals blah, 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 blah. I can take summation of the AI coefficients times a to the d minus I times something. So I have here summation I from 1 to d, AI, a to the d minus I, xt minus d, plus summation I, and then a bunch of coefficients here. I'm just going to call it mi. Mi ut minus I. I go from 1 to d. There are some coefficients here which I don't really care what they are, but they're only d terms. They're no more than d terms. Good. So now, what can I say about this thing here? This is a to the d, right, by Cayley-Hamilton, because it's exactly this. I basically took Colmann's combination according to the coefficients of the Cayley-Hamilton. So it's equal to a to the d. Okay? I don't need to know what these AI are. I'm just doing it for analysis. Okay? I'm just taking combination of these equations according to the Cayley-Hamilton coefficient. That's what I'm doing. There exists. I don't know what they are. So this is a to the d. There is a negative here. And if this is a to the d. So now let's take this equation and this equation and add them up. Okay? What do I get? This term here cancels out. Okay? So I get xt minus summation I AI xt minus d minus I, sorry, equals some summation I from 1 to d mi ut minus I. Everyone agrees? So let's shift side and multiply by c. So I get yt summation I from 1 to d ai, which are times xt yt minus I, plus summation j from 1 to d and j hat ut minus j. And that's what I wanted to show. I multiplied by c here.
So I guess it then seems very similar to what we did before. So instead of just doing the linear term being just the sum of the UIs,
Yeah.
you incorporate T of memory
Yes.
because your matrix
Not T,
has
not
rank
T,
T.
D,
Oh,
D.
sorry, T of memory.
Yes.
Because your rank is D D, and when you multiply by the A to the I, it keeps on being D. And then the Cayley-Hamilton kind of formalizes that for us, that you only need to go back in memory that much.
I only need to go back D in memory, yeah.
Oh, but you do need the YT. You cannot just.
I need the Ys. So the U's by itself, they're not enough. I need the Ys, but that's fine, I have them. In full observation, I have them. And this shows me I need D memory, but I get an efficient algorithm. The parameters of it do not depend on the dimension. There is something here that depends on the dimension, how far back I need to go, but that's relatively easy to resolve, okay? I kind of like, see, does it work? No, I take more memory, does it work? That's kind of an easy thing to resolve. So, it's not the same as reconstructing A. You agree with me? A is D by D, it's huge, I need to know what it is, I need to fill it, all the entries of this matrix, that's a much harder thing to do, and it's not convex. This is all convex, on gradient descent, and very simple algorithm that is able to dynamically learn any linear dynamical system. Yeah, questions? Yeah, Jerry.
So I guess when you learn the coefficients A, I mean, that tells you information about the lambdas, right? So you could technically reconstruct your A.
Oh, I see. You're saying that if I learn these coefficients exactly,
Yeah.
maybe I can reconstruct the lambdas from it. That's a good point. So that I think it's true. So what happens is that these A's are related to the lambdas. For example, I believe the last one is the trace because the sum of all the lambda i's, right? If you just take degree 1, it's 1 multiplied by all the rest or something. So it's like, sorry, the x to the d minus 1. X to the d minus 1 is the sum of all the lambdas. Then I think the last one is like the determinant. And you can reconstruct the trace, the determinant, and various other moments and part of the reconstruction. I don't know that it's trivial because you still have, these A's are going to be very large, right? And they're going to be like all choice, n choose 2, d choose 2 over 2,
Yeah.
lambda, some of them, they're going to be exponentially large in the lambdas. So you might get huge numbers, A. B, it might be that small imprecision, because of that, small imprecision may cause large imprecision in the lambdas, especially if you have noise. But yeah, in principle, you could do that. I don't know why you would want to do it. I mean, at least up to diagonalization, you could reconstruct the A's. I agree with you. You have enough information there to reconstruct the diagonal variant of A. Not clear to me it's sufficient, but I think you have enough information. That is correct. The one other interesting thing is that happens here. Look, these are scalars. So we were saying that you need to learn a function of both u's and y's. The function of u's are matrices, d in by d out. The function of y's are just scalars. That's a very simple functional here. Okay? It's a very simple thing. And this, by the way, is an interesting thing. I don't know that we noticed that before. It's a very simple thing. So basically, d scalars and d matrices that are d in by d out. I don't know how you all feel about it. I think it's a very neat thing. You can do it without any further knowledge about the system. You don't know what it is, you don't know the state, you don't know anything. You can still convex learn such a sequence. Yeah?
Could you briefly state again why a to the d is equal to negative summation, so on?
Yeah, because summation of all of them plus a to the d is 0. Right? So sum of all of them, including, you see the coefficient of AD here, a to the power d is 1. That's what I said when AD is here is 1, where this person here told me a to the d is 1, the coefficient. So summation AI, a to the I is 0, and this is basically a to the d plus summation I from 1, from 0 to d minus 1 of the rest. So that's why I have this. It's up to d minus, from 0, maybe to 0, from 0 to d minus 1. It's not from 1 to d. Make sense? More questions? How come your all was so quiet about it? It's such a nice thing. Ask a question. Did I go too fast? Is this like what happened? Did I go too fast or what?
For the Cayley-Hamilton, if you can guarantee that the rank of A is smaller and you do the Jordan, can you get that polynomial to be? Basically, instead of having to go back these steps, you just need to go back rank of A steps.
Oh, you're asking if I have multiplicity of eigenvalues? I don't think so. But my intuition is not. The Cayley-Hamilton theorem is true even if you have multiplicity. So it's going to be x minus lambda I to the power of whatever multiplicity. But then the proof I showed you, this one-line proof doesn't work because you don't have diagonal, right? It's a Jordan form. But I think you can still do it with a Jordan kind of matrix here, and that will be fine. So you have Jordan block matrix. So you can, it's not diagonal, you can put it in Jordan form, but this. Then you wouldn't take the I here, you would take the Jordan, whatever. So that's still fine. I don't think that you will need memory less than full rank, and the reason is that if I do a very slight perturbation, then it's diagonal, right? Then I need full. Think of a very degenerate matrix, it's all the same eigenvalue. You take small perturbation, it has already D memory. So it does make sense to me that it has one if you kind of collapse it. That doesn't make sense to me. But I don't have a proof for you right now. Yeah?
One small technical thing on the indices.
Mhm.
Like, over there you said A sub I times big A d to the minus I. But then the AI here is defined to be the coefficient of AI. So like maybe you want to define the other AIs as like A sub d minus I.
You're saying I have a typo between AI and to the power? Yeah, you're right. That's right. So I think I need here, it should be A d minus I. The subscript should be A d minus I here. Yeah, you're right. But you see what I mean. So, okay. So you're right. I think I need to multiply this by A d minus I, or whatever corresponds to the power of A that will cancel out by the Cayley-Hamilton. More questions? Okay, so if no more questions, let's see where do we want to head from here. This is already a very interesting situation. Okay, I'm not controlling a dynamical system. I'm only predicting where it's going to go. But I'm able to do it extremely accurately and extremely efficiently with a very simple algorithm by Cayley-Hamilton. What's the biggest downside of this method? Yep.
You assumed it's linear.
Yes. Okay. That I'm going to resolve for you. But there is a bigger one. Yeah, Connor?
D can still be pretty big.
Okay, good. That's what I mean. So the D here can still be huge. Okay. So for a very complicated system, D can be, I don't know, I don't want to put a number on it, but it can be arbitrarily large. There's no reason for it to be small. You can have phenomena that go back a whole lot. And that is not resolved by Hamilton. It will be resolved by if I make an additional assumption, like Alex said. If I assume the spectral radius is bounded from above by something, then the effective memory goes down. But in general, I don't need to see the memory. That's just a fact. So there are systems, for example, here is a system. So xt plus 1 is A xt, where this A is a permutation over D elements, such as it brings the item from Diego to be first. So it would look like 1 here, and then 1, 1, 1, 1, 1 below the diagonal, and everywhere else 0. So A equals to this kind of dynamical system. What it does, it brings forward someone from D iterations ago to the future. And here you need D memory, clearly. There's nothing you can do about it. You need D memory. So in full generality, there's basically nothing you can do but suffer D. Nevertheless, this linear method suffers it in the least possible way. I mean, it just suffers it in you have an efficient algorithm, it's all low dimensional. Okay, number of parameters that can grow with the memory. That's one issue. The other is, so I'm going to show you next class, which is going to be next Tuesday, a method which doesn't have D and it's yet efficient. It's a much more sophisticated method, and it's called spectral filtering. It's kind of different technique. The other is, which you mentioned, Elijah, is nonlinearity. Nonlinearity actually is surprisingly amenable to linearization. And here what we're going to do is a similar trick to reinforcement learning. We're going to linearize the whole space. But if we have algorithms that do not depend on the dimension, linearizing the whole space is fine. Because even though the dimension grows, it's not going to affect our bounds or our methods. Okay, so to summarize, so up next, I'm going to talk about reducing dependence on D, and 2, nonlinear dynamics. When we talk about nonlinear dynamics, of course it has to be some restricted class because we already saw that some of them are NP hard, or it has to come into the bound somehow. So in full generality, it has to be hard. Okay? All right. As I said, Thursday no class, and I'll see you all next Tuesday.